front of it, above it. Always put this element above it. Okay, to remind yourself, this is a vector. I have to be super careful. Okay. So next, I want to move on to 15.2, which is called line integral. Okay, which is called line integrals. So line integrals, I basically want to talk about this in R2 and in R3. Okay, so first of all, I have to know what a line is mathematically in R2 and in R3. So if it is in R2, this can be a line. Okay, this can be a line. We defined a line before as a graph of a function. All right. So for instance, this can be a graph of y equals f of x. All right. But this is another very general. For instance, I can have this kind of curve, which is not going to be a graph of a function anymore. All right. This is not a graph of function because if you find one input, you're getting multiple outputs. So this is not going to be a graph of a function anymore. So using the graph of a function to define what a line is pretty restrictive. You agree with me? Yeah. Using the graph of function to define what a curve or what a smooth line is on R2 is pretty restrictive. Here, by using vector and vector functions, it's going to be much more general. So I would define a line is a vector function when I have one independent variable. Okay? So any smooth curve, or more generally speaking, lines on R2 is a vector function when you have one independent variable. You can understand this variable as a time variable. You can understand this as a time variable, which means on a fixed curve, given a time, I have a point on this curve. All right? I will have a point on this curve. So if I line this point with the origin, I'm getting a vector. Amen? So if I change the time continuously, then this point will change continuously on the curve, which means this vector will change continuously according to time. Am I right? So these two are equivalent changing. If I change the vector continuously, I'm also changing the point continuously, and therefore I will get a smooth curve. So using this vector function to define what a curve is much more general. It will work for this kind of curve as well. So for instance, if I have a function defined by a vector with one time variable, then given any time I have a vector, which means I have a terminal point which is defined by this vector. All right? So if the time is changing, then the vector is going to be changing from one vector to the other vector, which means the terminal point will be changing from one to the other. If I change the time continuously, the vector will change continuously, which means this point will change continuously to form a curve. Okay? So using this definition to define what a curve is in R2 is much more general. You don't have to worry about whether it's coming from a function or not. Okay? That was me. For instance, I give you this example. RT is equal to cosine t sine t. What does this curve define? We learned this before actually. This is defining a circle. Right? This is defining a circle. One way you can see that is x component plus y component is equal to 1. This is actually defining a circle centered at the origin with radius 1. However, I was not being very precise here. Not only I have this time variable, I should also have an interval or domain for the time variable. For instance, if I allow t to go from 0 to 2 pi, I'll be able to get the whole circle. If I allow t to go from 0 to pi, for instance, I'm getting a half circle above x-axis. All right? If I allow t to go from, say, 0 to 4 pi, I go for the whole circle 1 time and 2 times. Right? So you can go for the circle for 2 runs by changing the different ranges for the independent variable t here. That was me. So by changing the ranges for the t variable, you can have different pieces on a curve. Are you with me? And we also talk about this very important concept about a curve defined by this t variable, which is the orientation. Do you still remember that? The orientation. So orientation is talking about a particular direction of moving on a curve. Okay? For instance, on this curve, I look at this range. It will cover the whole circle, but not only that, I can tell more information from this definition. If t is changing from 0 to 2 pi, when t is equal to 0, I have 1, 0. So it is beginning at this point. When t is equal to pi half, I'm ending up at this point. So this is actually not only defining the whole circle, but also defining the whole circle in a particular direction. So this direction is going counterclockwise. Okay? So the orientation is defined as one-way direction. Okay? It's a one-way direction on the curve such that if you allow t to increase, then you're getting a particular direction of moving the point on the curve. So for this particular case, I'm getting a counterclockwise whole circle coming from this range. Are you with me? So both of the orientation and the range of the independent variable t here is very important. We actually talk about several different vector function formulation for different curves. Before, I even called this as a parametric definition of a curve. Do you remember that? Mm-hmm. Right? A parametric definition of curve. In other words, I introduce a parameter t to define x component and y component separately. And this one, if you eliminate the t variable, you're going to get x squared plus y squared is equal to 1. Right? So if you eliminate the t variable, you're going to get x squared plus y squared is equal to 1. But when you do that, you lose two pieces of information. One piece is you don't know whether it is a whole circle, half circle, or even two runs. Okay? Especially these two runs. It's pretty hard to describe if you have this kind of equation. You don't know how many runs you have. That's the first thing. Second is you lose the orientation. Okay? But we do have a couple of more examples. For instance, if I have a curve is equal to a cosine t, b sine t, slightly different with the circle over there. What does this vector function define? It defines an ellipse with x-axis A and b-axis as y-axis as b. So you can eliminate t variable by this is equal to x, this is equal to y. So you can easily see x divided by a is equal to cosine t, y divided by b is equal to sine t. So if I square them and add them together, you can get 1. So this defines exact line ellipse with x-axis A, y-axis B. But again, if I'm doing this, I lose two very important information. I lose the runs, I lose the orientation. Okay? But you should be able to recognize a curve from both of these two representations. Okay, listen to me carefully. Being able to derive the parametric equation of different curves is so important in this whole chapter. We have to be able to do that to even begin our calculus. So if you have a curve which is written in this form, you should be able to derive its parametric form or the vector form. If you have a vector form, you should be also able to eliminate that parameter to write down it in this format as well. That's me? Mm-hmm. Questions? So I'll ask you the following question. I want to find RT as a straight line from 1, 1 to 26, 26. Okay? So if I have 2 points on R2, naturally I know there's a straight line lining them together. All right? So if I have 1, 1 and 26, 26, I know there's a line passing through these 2 points. And we all know how to find the equation of the line. All right? You have 2 points, you can easily find the slope, and then you have a point and a slope, you know what the equation looks like. All right? So the slope for this guy is equal to 26 minus 1, 26 minus plus is equal to 1. All right? and passes through 1, 1, you know the equation should be y equals x. All right? This is the easiest line equation ever. You know this is the equation that passes through 1, 1, and 26, 26. I want to find the parametric equation for this guy. How do you find the parametric equation? Okay, how do you find the parametric equation? The parametric equation for the vector function, the only thing you do is to introduce this one parameter t. You have to allow t to be equal to something related to both x and y. All right? So in this case, the easiest introduction of the additional parameters t is just equal to x. Right? It is equal to x, and then it is going to be equal to y as well. Okay, so this is going to be the parametric equation for the straight line. However, there's one thing missing here. When we have this equation, we don't have the range or the rods. We don't have the orientation. So if we write it in the parametric form, I'm supposed to have both of them. One thing I know, t has to be go from 1 and 26. Okay, which means I'm not going to be looking at the whole straight line because it is from 1, 1 to 26, 26. I have to delete both of these two ending pieces. So it's going from 1, 1 to 26, 26. Not only that, I should also be able to tell the orientation from 1, 1 to 26, 26. Whereas t is increasing, the points are moving from this point to this point. So this is the orientation here. Because every time you have a segment of a line, you have one direction and the other direction. This equation doesn't tell you that. All right? This equation doesn't tell which direction it is. But this direction will be reviewed from the vector field. I'm sorry, the vector function right here. Okay? So as long as we have this preparation, I want to define what the line integral is. So given a line, or strictly speaking, should be a smooth curve, C defined RT is equal to XT, YT. You learn about the arc length of the curve. Arc length of a curve. How to find the arc length of a curve. It's not really a surprising formula. The arc length of the curve going from the initial point A to terminal point B is equal to the integral from A to B square root of x prime t squared plus y prime t squared dt. Have you learned this before?
Yes.
Yeah.
So this is the arc length of a curve defined by this vector function going from the initial time t equals a to t equals b. So this is the formula. I can rewrite this formula from a to b r prime t dt. Okay? Whereas this derivative hitting the vector function is defined as taking the derivative for each one of them separately. Okay? So if I have a vector function, I can take the derivative, which is just the x derivative, component derivative, and y component derivative. So this square root of x component square plus y derivative component square is nothing but the length of this vector. All right? So you can rewrite it in this easier form, but they're talking about the same thing. Especially if you're doing computation, you're always using this guy. Okay? So the arc length is nothing but a one variable integration. Okay? So one thing I want to immediately do is find the application here. So in this class, by using calculus, we have accomplished the following two. We were able to compute the area of a disk. We're able to compute the volume of a hole. We can also compute the arc length of a circle, right? We can also compute the arc length of a circle. So arc length of a circle is exactly taking the line integral of this function, cosine t, sine t. I want to include the whole circle, so t is going from 0 to 2. 2 pi. All right? So this is one immediate application of the arclength computation. So the circle has the length from 0 to 2 pi. Square of cosine square, cosine prime is equal to minus sine t. All right, by using the formula. So this is xt, this is yt, so I'm taking the x prime t here. Okay? I also need to take the y prime t. So y prime is going to be cosine t squared. Okay? And then dt. So I have sine squared plus cosine squared. That's the highlight of my whole career. Every time I see this, I'm happy. Cosine plus sine is creating a 1, so this is from 0 to 2 pi. You're integrating a constant function 1. That's why you get a 2 pi. Right? So this is the length of a circle with radius 1. Okay? So now we have accomplished one-dimensional circle, two-dimensional disk, and three-dimensional ball. We will be able to find the arc length, the area, and the volume. If you look at this calculus, right, it took probably 1,000 years for the Asian people to even figure out the formula, but for calculus, it's a two-line computation. So I want to mention this computation works for any vector function, right? Not only the vector function for the circle. Given any vector function, it defines a piece of a curve. By using this formula, you should be able to find the arc length. Everything? You'll be able to find the arc length. Not only that, we can also define a line integral of a scalar function. On a curve. C is defined by RT. T goes from A to B. Okay? So this is what our main object today. So the main object here is a line integral of a scalar function on a curve. Okay? Which means there are two conditions here to even begin doing the integral. I have to have a curve. Right? I have to have a curve.